Adjustable speed drive or variable speed drive describes equipment used to control the speed of machinery. Many industrial processes such as assembly lines must operate at different speeds for different products. Where process conditions demand adjustment of flow from a pump or fan, varying the speed of the drive may save energy compared with other techniques for flow control. Where speeds may be selected from several different preset ranges, usually the drive is said to be adjustable speed. If the output speed can be changed without steps over a range, the drive is usually referred to as variable speed. Adjustable and variable speed drives may be purely mechanical, electromechanical, hydraulic, or electronic. Basic electric motor drive alternatives. AC electric motors can be run in fixed-speed operation determined by the number of stator-pole pairs in the motor and the frequency of the alternating current supply. AC motors can be made with one or more stator-pole pairs, the number of which determines the motor's synchronous or asynchronous speed being defined as where N is synchronous speed in RPM, F is frequency in Hertz and P is number of poles. The number of such fixed-speed operation speeds is constrained by cost as number of pole pairs increases. If many different speeds or continuously variable speeds are required, other methods are required. Direct current motors allow for changes of speed by adjusting the shunt field current. Another way of changing speed of a direct current motor is to change the voltage applied to the armature. An adjustable speed drive might consist of an electric motor and controller that is used to adjust the motor's operating speed. The combination of a constant speed motor and a continuously adjustable mechanical speed changing device might also be called an adjustable speed drive. Power electronics-based variable frequency drives are rapidly making older technology redundant. Reasons for using adjustable speed drives, process control and energy conservation are the two primary reasons for using an adjustable speed drive. Historically, adjustable speed drives were developed for process control, but energy conservation has emerged as an equally important objective. Adjusting speed as a means of controlling a process equals. The following are process control benefits that might be provided by an adjustable speed drive: smoother operation, acceleration control, different operating speed for each process recipe, compensate for changing process variables, allow slow operation for setup purposes, adjust the rate of production, allow accurate positioning, control torque or tension, allow catching of spinning load after outage. Example. An adjustable speed drive can often provide smoother operation compared to an alternative fixed-speed mode of operation. For example, in a sewage lift station, sewage usually flows through sewer pipes under the force of gravity to a wet well location. From there it is pumped up to a treatment process. When fixed-speed pumps are used, the pumps are set to start when the level of the liquid in the wet well reaches some high point and stop when the level has been reduced to a low point. Cycling the pumps on and off results in frequent high surges of electric current to start the motors that results in electromagnetic and thermal stresses in the motors and power control equipment. The pumps and pipes are subjected to mechanical and hydraulic stresses, and the sewage treatment process is forced to accommodate surges in the flow of sewage through the process. When adjustable speed drives are used, the pumps operate continuously at a speed that increases as the wet well level increases. This matches the outflow to the average inflow and provides a much smoother operation of the process. Saving energy by using efficient adjustable speed drives. Some adjustable speed-driven applications use less energy than fixed-speed operated loads. Variable torque centrifugal fan and pump loads are the world's most energy-intensive. Since most of the energy used for such fan and pump loads is currently derived by fixed-speed machines, use of efficient adjustable speed drives for these loads in retrofitted or new applications offers the most future energy savings potential. For example, when a fan is driven directly by a fixed-speed motor, the airflow is invariably higher than it needs to be. Airflow can be regulated using a damper, but it is more efficient to directly regulate fan motor speed. According to affinity laws, motor-regulated reduction of fan speed to 50% of full speed can thus result in a power consumption drop to about 12.5% of full power. Types of adjustable speed drives. Speed adjustment techniques have been used in transmitting mechanical power to machinery since the earliest use of powered machinery. Before electric motors were invented, mechanical speed changes were used to control the mechanical power provided by water wheels and steam engines. When electric motors came into use, means of controlling their speed were developed almost immediately. Today, various types of mechanical drives, hydraulic drives and electric drives compete with one another in the industrial drives market. Mechanical adjustable speed drives There are two types of mechanical drives, variable pitch drives and traction drives. Variable pitch drives are pulley and belt drives in which the pitch diameter of one or both pulleys can be adjusted. Traction drives transmit power through metal rollers running against mating metal rollers. The input-output speed ratio is adjusted by moving the rollers to change the diameters of the contact path. Many different roller shapes and mechanical designs have been used. Hydraulic adjustable speed drives There are three types of hydraulic drives, those are, hydrostatic drives, hydrodynamic drives and hydroviscous drives. A hydrostatic drive consists of a hydraulic pump and a hydraulic motor. Since positive displacement pumps and motors are used, one revolution of the pump or motor corresponds to a set volume of fluid flow that is determined by the displacement regardless of speed or torque. Speed is regulated by regulating the fluid flow with a valve or by changing the displacement of the pump or motor. Many different design variations have been used. A swash plate drive employs an axial piston pump and/or motor in which the swash plate angle can be changed to adjust the displacement and thus adjust the speed. Hydrodynamic drives or fluid couplings use oil to transmit torque between an impeller on the constant speed input shaft and a rotor on the adjustable speed output shaft. The torque converter in the automatic transmission of a car is a hydrodynamic drive. A hydroviscous drive consists of one or more discs or connected to the input shaft pressed against a similar disc or discs connected to the output shaft. Torque is transmitted from the input shaft to the output shaft through an oil film between the discs. The transmitted torque is proportional to the pressure exerted by a hydraulic cylinder that presses the discs together. Continuously variable transmission Mechanical and hydraulic adjustable speed drives are usually called transmissions or continuously variable transmissions when they are used in vehicles, farm equipment and some other types of equipment. Electric adjustable speed drives Types of control. Control can mean either manually adjustable, by means of a potentiometer or linear Hall effect device, or it can also be automatically controlled, for example by using a rotational detector such as a gray code optical encoder. Types of drives. There are three general categories of electric drives: DC motor drives, eddy current drives and AC motor drives. Each of these general types can be further divided into numerous variations. Electric drives generally include both an electric motor and a speed control unit or system. The term drive is often applied to the controller without the motor. In the early days of electric drive technology, electromechanical control systems were used. Later, electronic controllers were designed using various types of vacuum tubes. As suitable solid-state electronic components became available, new controller designs incorporated the latest electronic technology. DC drives. DC drives are DC motor speed control systems. Since the speed of a DC motor is directly proportional to armature voltage and inversely proportional to motor flux, either armature voltage or field current can be used to control speed. Several types of DC motors are described in the electric motor article. The electric motor article also describes electronic speed controls used with various types of DC motors. Eddy current drives. An eddy current drive consists of a fixed-speed motor and an eddy current clutch. The clutch contains a fixed-speed rotor and an adjustable speed rotor separated by a small air gap. A direct current in a field coil produces a magnetic field that determines the torque transmitted from the input rotor to the output rotor. The controller provides closed-loop speed regulation by varying clutch current, only allowing the clutch to transmit enough torque to operate at the desired speed. Speed feedback is typically provided via an integral AC tachometer. Eddy current drives are slip-controlled systems, the slip energy of which is necessarily all dissipated as heat. Such drives are therefore generally less efficient than AC-DC-AC conversion-based drives. The motor develops the torque required by the load and operates at full speed. The output shaft transmits the same torque to the load, but turns at a slower speed. Since power is proportional to torque multiplied by speed, the input power is proportional to motor speed times operating torque, while the output power is output speed times operating torque. The difference between the motor speed and the output speed is called the slip speed. Power proportional to the slip speed times operating torque is dissipated as heat in the clutch. AC drives. AC drives are AC motor speed control systems. A slip-controlled wound rotor induction motor drive controls speed by varying motor slip via rotor slip rings, either by electronically recovering slip power fed back to the stator bus or by varying the resistance of external resistors in the rotor circuit. Along with eddy current drives, resistance-based WRIM drives have lost popularity because they are less efficient than AC-DC-AC-based WRIM drives and are used only in special situations. Slip energy recovery systems return energy to the WRIM stator bus, converting slip energy and feeding it back to the stator supply. Such recovered energy would otherwise be wasted as heat in resistance-based WRIM drives. Slip energy recovery variable speed drives are used in such applications as large pumps and fans, wind turbines, shipboard propulsion systems, large hydro pumps, generators and utility energy storage flywheels. Early slip energy recovery systems using electromechanical components for AC-DC-AC conversion are termed Kramer drives, more recent systems using variable frequency drives being referred to as static Kramer drives. In general, a VFD in its most basic configuration controls the speed of an induction or synchronous motor by adjusting the frequency of the power supplied to the motor. When changing VFD frequency in standard low-performance variable torque applications using volt per Hertz control, the AC motor's voltage-to-frequency ratio can be maintained constant, and its power can be varied between the minimum and maximum operating frequencies up to a base frequency. Constant voltage operation above base frequency, and therefore with reduced volt per Hertz ratio, provides reduced torque and constant power capability. Regenerative AC drives are a type of AC drive which have the capacity to recover the braking energy of a load moving faster than the motor speed and return it to the power system. The VFD article provides additional information on electronic speed controls used with various types of AC motors. See also, continuously variable transmission, regenerative variable frequency drives, variable frequency drive, DC injection braking, doubly fed electric machine. References: Spitzer, David W. Variable speed drives. Instrument Society of America. ISBN 1-55617-242-7. Campbell, Sylvester J. Solid-State AC Motor Controls. New York, Marcel Decker, Incorporated. ISBN 0-8247-7728-X. Jishk, Ralph L. Controlling Power Transmission Systems. Cleveland, Ohio, Penton IPC. Siskind, Charles S. Electrical Control Systems and Industry. New York, McGraw-Hill, Incorporated. ISBN 0-07-057746-3.